So now proof of theorem 35, and I'll spell it out explicitly before actually proving it. You have two isomorphic groups, G and H. The mapping F maps G to H. And the question, well, there are two parts to this proof. One is you're asking the question and proving it that the unit in G, this is G and this is H, these are the group tables, group table of G and group table of H. Now the unit of group G, question, does it map with F so that the mapped E, in other words F of E, is that the same thing as the unit of the group H? So we're trying to prove that F of E equals the unit of H. Okay? So we'll try to prove that. And in the process of the proof, very probably, certainly, we will use this form. This is the criterion needed to ensure that elements of the two group tables map to each other, that they map. Okay, so we'll use this form in the proof. Right? So we're trying to prove that this unit, the unit of G and the unit of H, so I put an H here, suffix. You have to try to prove that this unit and this unit map. So this one maps to that. So we're trying to show that F of E equals the unit of H. That's what we're trying to prove. So 35 part 1, if you like, is show that F of E equals the group H's unit. We have to show that. All right, and we'll use this kind of formula. Well, I'll straight out of the text. So we'll start with the left-hand side. We'll start with F of E and just play with it and see if we can prove this. So let's see. So F of E. So we just square it. So we just square this thing. Now this will be, now FF, that's of this form, right? So FF is, so F of E times F of E will just be equal to F of EE, right? Using this, so let's do that here. So this will be F of EE, okay? And EE, they're both units, so that's just E, so this is just equal to F of E. Okay? So we know that. And now let's pre-multiply on both sides, this side and this side, left-hand side, right-hand side, by the inverse of F of E. So okay. That's obviously the inverse of this. Right? G and H, they're both groups, and if you have an F of E here, it will have an inverse because it's a group. Yeah, so this is a member of a group. Okay, so F of inverse, F of E, F of E. And that's just this, pre-multiplied by that. Now this will cancel, right? Well, let's apply this to this side as well. So I'll draw an arrow so you know where it's coming from. So this is again the inverse. Right? We're multiplying both sides on the left by the inverse. So F of E. Now, what is this and what is this? Well, This f of e, which group is it in? Well, it's here, right? It's in group H. So the inverse times itself will just be the unit, but which unit? Well, it's the unit. See, these two here, f inverse and fe, they both belong to group H. So this will just be the unit. So this will be the unit in H. Okay? Times f of e. And this will just be, yeah, it's just the same as this. It'll just be e of h. Alright? See where we're going with this now? Alright. These two elements both belong to group H. Now the unit times something is just something. So you've got f of e equals e of h, as was to be proved. And then I could put a little end of proof marker here. Although in Barnard he tends to do it like this. He fills in this vertical rectangle. That's his end of proof marker or sign. Many textbooks, many authors nowadays, they don't fill it in. It's just like a hollow vertical rectangle. The end of proof. What in the old days often you'd write QED. Quod erat demonstratum, which means as was to be proved. Okay? So that's the end of the proof. Right? Now, so the second part. So that's proof of part one. Now part two is a similar type proof, but about the inverses. So here's an arbitrary element of G. Just call it x. Little x. It's an element. Here's its inverse. Now x will map to f of x, and this inverse here will map to f of the inverse. But this element here, f of this inverse, is it the inverse of this one? See, x maps to that, and the inverse of this one maps to this. But is this one the inverse of that one? So question mark, is this the same as this? If it is, then the inverses map. Now the units map, the unit of G mapped to the unit of H. G and H are isomorphic. So your suspicion is, and there's a hunch, if you're a mathematician you probably think, well, probably the inverses will also map if the two groups are isomorphic, right? If they're the same group, they should map. So therefore this, if you map the inverse here in group G, you should get something that is the inverse of this one in group H. Right? So the inverses should map. So part two boils down to proving that the mapped inverse, this one, is equal to the inverse of the map. Put it that way. So the map of the inverse is equal to the inverse of the map. Right? So let's now try to prove this. So show f of x inverse equals f of x, the inverse of that. That's what we have to show. That's what we have to prove. All right. So we're talking like f of x. Now again, we'll use this formula, and we're not talking about e's anymore. We're just talking about x's. So we'll put x's for these m's and n's. So I'll maybe get one more line here. So let's start off with f of x inverse. You may ask, where does this come from? Well, it works. Right? Now, this is of the form here. So we can take these two and put them together. So this will be Because why can we do this? Because we're told that this mapping, G to H, is isomorphic. Right? These two groups are isomorphic. And if they are isomorphic, we can do this. This is one of the criteria of isomorphism. This one, this formula. All right. So what is this? So you just bring these two together. So you'll get f x inverse x. Okay. And that is what? Well, these x and little x and lex inverse, they're both members of the set of the group G, right? And the inverse of the something of itself is just E, and that's the unit. That's the unit of G, the first group. Okay, that's f of E. But we know f of E. We just proved it before. But f of E is just E of H. Okay. We know that's true. All right. Now, so why did I do that? Well, look, I don't know, let's say if y is the inverse